Yeah, thank you very much for introduction. I would like to thank the organizers for giving me an opportunity to talk this conference. The title is MTF equivalences on the real Grothendieck groups. Yeah, so this talk is based on joint work with Osamu Iyama. This is updated recently on archive. Okay, yeah, so in this talk, the category A is an abelian category of finite length with exactly n isoclasses of simple objects. And in this talk, we mainly consider the dual real Grothendieck group, K0 A R star. That is the real Grothendieck group in the title. Of course, it is identified with the n-dimensional Euclidean space, Rn. In my sole previous work, I introduced an equivalence relation on K0A R star. So this is called the TF equivalence. So the TF equivalence contains much useful data of the category A. And moreover, it's related to many things, such as the semi-stable subcategory, the semi-stable torsion pairs, the word chamber structure on K0A R star, and the G-vector form of two-term preceding complexes if we consider the module category of finite dimensional algebras. And what we did in our study is introducing the MTF equivalence for each object M in A. The purpose is to coarsen the TF equivalence in a systematic way, of course, preserving representation's theoretical meanings. Yes, so we first give the precise definitions of semi-stable torsion pairs. So first, note that each element theta in K0A R star is an unlinear form from K0A R to R. Therefore, for each object M in A, so we have some real number denoted by theta of M. Then for each theta, we have two semi-stable torsion pairs denoted by T bar theta F theta and T theta F bar theta. And T bar theta is a torsion class consisting of all objects M, such that for any quotient n of M, theta n is 0 or positive. And the corresponding torsion-free class F theta is the full subcategory consisting of M, such that for any non-zero subobject L of M, theta of L is strictly negative. And similarly, T theta and F bar theta are defined. And they satisfy the conditions of torsion pairs, which appeared in Emine's talk. In my previous work, I defined theta and eta TF equivalent if and only if T bar theta F theta coincides with the torsion pair T bar eta F eta. And moreover, T theta F bar theta coincides with T eta F bar eta. Now I give an easy example of TF equivalences. So let A be the path algebra of the A2 quiver and carry A be the module category of this path algebra. And then we can check that there are exactly 11 TF equivalence classes in K0A R star given by in this picture. The first one is the origin itself. And from the origin, there are 5 half lines, which are TF equivalence classes, and the remaining 5 are open sets or chambers in the dual real Grothendieck group. Next we explain the ingredients to define MTF equivalences. So let M in A and theta in K0A R star. Then, as I said, so we have two torsion pairs, T bar theta F theta and T theta F bar theta. So therefore, so we have two short exact sequences. The first one is 0, T bar theta M, F theta M, 0. So T bar theta M belongs to T bar theta, and F theta M belongs to F theta. And similarly, we have another short exact sequence. And the point is that so the torsion class T theta is contained in the other torsion class T bar theta. Therefore, T theta M is a sub-object of T bar theta M. Thus, we can set W theta M as the quotient of T bar theta M by the sub-object T theta M. And actually, so this belongs to the intersection of T bar theta and F bar theta, which is denoted by W theta. Yeah, actually, W theta is nothing but the full subcategory consisting of all theta semi-stable objects in A. Yeah, and it is known that W theta is an abelian category of finite length again. So therefore, we can set sub theta W theta M as a set of all composition factors of W theta M in W theta. Now we can say the definition of MTF equivalences. Fix an object M in A. Then we say that theta and eta are MTF equivalent if the following two conditions hold. Yeah, the first one is similar to the original TF equivalence. Yeah, T bar theta M, F theta M coincides with T bar eta M, F eta M. And moreover, T theta M, F bar theta M coincides with T eta M, F bar eta M. And we remark that then we have W theta M coincides with W eta M. And in the other condition, so we compare their composition factors in W theta and W eta. Yes, namely sub theta W theta M coincides with sub eta W eta M. And thus we set TFM as a set of all MTF equivalence classes and theta M as a set of their closures. And then we have that we have bijections between TFM and sigma M. Yeah, so taking closures and taking the relative interiors. And moreover, sigma M is a finite, complete, generalized form in K0 R star. So we use the term generalized because cones in sigma M are not necessarily strongly convex. Yeah, so may contain some non-zero vector subspace. Yeah, and so now I show an easy example of MTF equivalences. So I use the same algebra and let M be the indecomposable projective injective model denoted by 1, 2. Then there are 7 MTF equivalence classes. The first one is the origin again, and there are 3 half lines from the origin. And the remaining 3 are open sets of K0 R star. And we remark that in order to make sigma M a fan, we must distinguish 1 and 4. So this is the reason why we assign the condition on composition factors. And actually, our result in the previous slides follows from a stronger result on relationship with Newton polytopes. Yeah, for each object M in A, its Newton polytope is defined as the convex hull of the set consisting of L in the real Grothendieck group, K0AR, not K0AR star. Yeah, and where we consider all sub-objects L of M. And we showed that sigma M is a normal form of the Newton polytope. That means we have bijections between sigma M and the set of faces, the set of non-empty faces of the Newton polytope. Yeah. To define these bijections, we use the maximum value of theta in the Newton polytope Nm. Now, I end my talk with an example of these bijections. So we use the same setting as the previous example, and then so as you saw, the left one is sigma M. So which have 7 elements, and the right one is the Newton polytope of M. Yeah. So Nm has exactly 7 non-empty faces, and the numbers show correspondence between sigma M and face Nm. Yeah. So these bijections are order reversing and convert dimensions to codimensions. Yes. Thank you very much.